today we're going to talk about exact differential equation. So this is unit 4 of the syllabus, differential equation. Okay, so let me write like this. Differential equation, we have studied about how to remove the first derivatives from a linear second order differential equation and how to solve it by removing the first derivatives, or to solve the homogeneous equation we introduce the independent variable z such that e power z is equal to x, or z is equal to log x. So those are similar. So now we will come to the topic exact differential equation. So exact differential equation. So what do we mean by exact here? So we know that the second order linear differential equation is written like d square y dx squared plus p dy dx plus qy equals r. Alright, here p, q, r are functions of x only or constant. So this is the second order linear differential equation. This is the standard form how we write it. But now we are going to talk about the exactness. So when do we say that this equation is exact? So we say that an exact differential equation is this type of equation if it can be obtained by differentiating its lower order of differential equation. Like suppose we have suppose we have this equation like 3y squared d squared y dx squared plus 4y say dy dx whole squared plus 6 dy dx whole squared is equal to x squared plus c. So suppose we have this equation, and if we differentiate this one with respect to x, then we will get, what will we get? 3y squared d cube y dx cube, right? dx 3 plus 4y, now we will have 8 y dy dx d square y dx squared plus, so this will become 12 dy dx d square y dx squared equals 2x. Alright, so if we have this equation here, 3y squared, this type of equation, so if we differentiate it with respect to x, then we obtain this equation, right? 3y squared d 3y by d x3, yes, and so on. So we call this equation, the second equation, exact because it can be obtained from differentiating this equation without any further process. So those type of equations that can be obtained without any further process by differentiating that equation, then we call that equation an exact differential equation. And we cannot always jump to conclusion like that, because we may not be able to find so easily like this. So we need some conditions. So how to check the exactness? So we will see this not as a theorem, but from the example itself. And let me write this. Suppose we have this p naught dny dxn. So this is the nth order plus, and p naught, these are the coefficients, constant or functions of x. So p1 dn minus 1y dx n minus 1 plus, and so on. So we will end up with p and y, right? P and y is equal to q. Suppose we have this. So we have the nth order differential equation and the coefficients p naught, p1 up to pn. So we will have the exactness condition if from the last one pn minus 1 first derivative here plus, so you will put the sign alternative and so on. So the last one may be, okay, let's put just plus or minus this one. So the last one would be p naught, what would be the derivatives? It would be n, right? So the nth derivative of that first coefficients. So if this is 0, then we call the differential equation exact. Okay, so this is the condition which is very important. So here pn minus 1 up to p naught are the coefficients of our derivatives in the differential equation, and we put the sign alternatively. So the first one minus, and then second one plus, and so on. And the first one we just take it as it is, and then the second one we put the first derivatives, and then after all, second derivative and third derivative and nth derivative. So if this equation becomes 0 when solving it, then we call the differential equation, the given equation, exact. So let's see an example here. Suppose we have the equation which is to be solved is, right, 1 plus x squared d 3y dx3 plus 3 plus 6x d square y dx squared plus 6 dy dx is 0. So we are asked to solve this differential equation. So like we said always, solving differential equation is not easy. And here what we need to solve is for y. So what value of y should we put to get this differential equation become 0? So solving this, let's solve it by exactness. Okay, so exactness would be, come here. So as we have seen before, I think we can see that this is p naught and this here, okay, let me change the color. This is p naught, this is p1, and this one is p2. All right, and so we don't have y, so Yeah, instead of writing this, we can just put here that plus 0y equals 0, because the without derivative should be there also in the standard form. So this one would be our P3. So we have P0, P1, P2 and P3. So to solve this, what we need to do is we take the last one, which is P3 first. So P3 minus P2 first derivative plus P1 second derivative minus P0 third derivative. So this should be equal to 0 if the condition is exact. So that means if the order is 3, the highest order in our given problem is 3, then we have to take the 3 times 3 times derivatives, right, for that coefficient. So what does this mean is that suppose P0 is the coefficient of this third order derivative. So that means this P0 we have to differentiate it 3 times. And likewise, here we have P0, P1, 3 plus 6x, and this is the coefficient of the second order derivative. So that means this P1 we have to differentiate it 2 times. We have to find the second derivatives, and so on. So we put that the sign alternatively, like we said before. So if this condition is satisfied, then we say that this differential equation is exact. So let's see, what is P3 is 0, P2 6, and if we differentiate it with this one, so we get 0. And then P1 is 3 plus 6x, differentiated 2 times, and we'll get 0. And 1 plus x squared, this is P0, and this is the coefficient of the third order. So that means we have to differentiate it 3 times. So if we differentiate it 3 times, so we'll get 0 again. So this condition is satisfied. This condition is satisfied. So we can check. So the condition is exact. All right. So what do we do? Now we can check that if the condition is exact or not from the given problem, right? So how can we solve this? If it is exact, then how to solve it? That one we have not talked it yet. So first, you have to prove that the condition is exact or not. So after that, what would come? So after this, we have to check that before that we said a differential equation is said to be exact if it can be obtained from its lower order, right, by differentiating it without any further process. So that means if the equation is exact now, then we can reduce this third order differential equation to second order. So how to do that is we have to write like this. So P0 now d square y by dx squared. So the first one, the given problem is d3y. So its order is 3, and now since it is exact, we can reduce to this lower order. So after differentiating this, then we'll get the same one again, right, if it is exact. And then here, so the coefficient would be P1 minus P0 prime, which is the first derivatives of P0, and dy dx, and then plus p2 minus p1 first derivative plus p0 second derivative y, which is equal to, and then we integrate it, right? We have to integrate the right hand side, which is 0, but if we integrate it, then it becomes 0 plus some integration constant, which let's call it c1. So we get this. So the key point here is we have to put the first coefficient, which is p0, just the same, and then after that we have to subtract and add alternatively for the coefficient of the derivatives here in the equation from its successor. Like after p0, the first coefficient is p1, so in the second coefficient we get p1 minus that p0 derivative, first derivatives, and then after that from p2 minus p1 plus p1 first derivatives and then p0 second derivatives. If there is any other coefficient which should be there, then it would be p3 minus p2 first derivative plus p1 second derivatives minus p0 third derivative, and so on. So we'll get this one. So if we put the value of p0, p1, p0 prime, and so on, so we will get, okay, let's see, 1 plus x squared is p0, and here is second order, plus, so our p1 is 3 plus 6x, and p0 prime is minus 1 minus 2x, right? So this is dy, sorry, dx plus our p1, p2 is 6, then p1 prime would be 6, then p0 second derivative would be just 2, right? 2, y equals c1. Okay, now we will check the exactness again. After solving this, simplifying this, we will get what here? This is just the same. So here we will get 3 minus 1 is 2, 6x minus 2x is 4x. So that means here we will get 2 plus 4x dy dx, right? And here we can get 6 minus 6 is 0, so 2y, just 2y. So here we can write 2y equals c1. So now we will check it again. While checking it, we can have here our p0 now. Let's see. Our p0 is here. Here is p1 and here is p2. Now we can check the exactness, like p2 minus p1 prime, which is the first derivative, plus p0 double prime, right? Second derivative. If this is 0, then we say that this reduced differential equation is exact again. So let's see. p2 is true. p1 first derivative would be 4. So 2 minus 4, which is minus 2. And p0 second derivative is 2. Right here. This will only be there in the second derivative. In first derivative, we will get this one also, but for second derivative, that one would become constant and it would be, the derivative would be 0. So that means minus 2 plus 2, which is again 0. So this equation is satisfied, and we can say that this differential equation is also exact. So if it is exact, then we can reduce it to the lower order again, right? So when reducing it, we will integrate the right hand side, and then we will get what? So what we will get is P naught dy dx, because now our problem here becomes second order, and if it is exact, then it will become first order now. All right, so P naught dy dx plus, what do we say, P1 minus P naught prime, right, first derivative, and then here y. So next would be the right side would be C1, which if we integrate it, it would become C1x plus some integration constant, which we call it C2. So here, if we put the values of these again, so we will get 1 plus x squared here dy dx plus, what is P1? So our P1 is here 2 plus 4x, and P naught prime would be 1 plus 2x. Because P naught, if we differentiate it, it would become 1 plus 2x here. And P1 is 2 plus 4x. So 2 plus 4x minus 1 plus 2x, right? Here, 2 plus 4x minus 1 minus 2x, y, which is C1x plus C2. Now if we solve this, then we will get 2 minus 1 is 1, 4x minus 2x is 2x. So 1 plus 2x, right? Instead of writing this, we can have 1 plus 2x. Now we'll check if this is exact or not again. So if it is exact, we can reduce it to its lower derivative, which would be no derivative at all. So that means if we differentiate it, we integrate it, okay? When reducing it, we integrate the whole thing. Here, from d to y, this equation, we find it as exact, so we integrate the whole thing. When we integrate the whole thing, the order becomes less and less. So here we get this, and then here we have, this is P naught again, and this is P1. So we have P naught and P1 only. So let's check if P1 minus P naught prime is 0 or not, right? So P1 is just 1 plus 2x, and then P naught prime would be this one. If you differentiate it, it would become 0. This x, it would become 1. This x squared, it would become 2x. So 1 plus 2x. But if you subtract, 1 plus 2x is P1 minus P naught prime would be 1 plus 2x, which is clearly 0, right? This one is 0. This one is 0. So P1 minus P naught prime is 0. So that means the condition for exactness is satisfied again. So if we integrate this whole thing again, we will get P naught y only, which is equal to, in the right side we got C1x plus C2. So if we integrate this, then we get C1x squared by 2 plus C2x plus C3, right? So if we put the value of P naught, which is 1 plus x squared, then y, which is equal to C1x squared by 2 plus c2x plus c3. So you are supposed to find y, right? We are supposed to find y. So that means if we just change the sides here, y is equal to 1 by 1 plus x squared into c1 x squared by 2 plus c2x plus c3. Right, so this is the final answer. This is the final answer for our question, our given problem. So like that, we have to see that the given problem is exact or not, and if it is exact, then we can integrate the whole equation to reduce it to its lower order, and then do the same process, so and so on. So some given problems may not be like this. Some may stop being an exact differential equation in some steps. So no problem with that. We can solve that thing by other process, other method also. So here let me say that again. First, an exact differential equation is a differential equation which can be obtained. All right. So yeah, an exact differential equation is a differential equation of any order which can be obtained by differentiating, I don't mind my handwriting, which can be obtained by differentiating its lower order. All right, so let me just say it informally, its lower order. This is informal, lower order, without any further process, without any further process. So if we can differentiate some differential equation and we get its higher order, then that higher order is always exact. So when checking the differential equation is exact or not, we use the coefficients of their derivatives, right? So the derivatives, how many times the derivatives that we take depends on the highest order of that equation. So if suppose P naught, like we said before, is the coefficient of the third order derivatives, and then P1 is the second order coefficient, and then P2 is the first, and P3 is no derivative, just the function y, which is equal to here 0 maybe. So while checking that it is exact or not, this given equation is exact or not, we checked this P0, P1, P2, and P3. So if there is no y in our given problem, then P3 would become 0. And likewise, if dy dx, the first derivative, is not there in the given problem, then P2 is 0, that means. But you have to consider those things. So while checking, we take the last one, which is no derivative, from no derivative, so P3, and then change the sign to minus, then p true and take the first derivative, then plus. Alternatively, you put the sign, you change the sign. So after p true, it becomes p1, right? It is in decreasing subscript. So p1, but you have to take second derivative, because here p3, why we don't take the derivatives is because there is no derivative. The coefficient is, it is the coefficient of no derivative, just the function. And p2, why we take first derivative here? Because p2 is the coefficient of the first derivative here. And why p1 we take second derivative here? Because it is the coefficient of the second order derivatives here in the given problem. And so on, it would be minus. So p naught is the coefficient of the third order derivative, so we take the third derivatives here. So if this sum and the thing becomes 0, then we say that this given problem, this given differential equation is exact. So if it is exact, then we can integrate the whole thing to reduce it to its lower, where it comes from. So while reducing it to its lower, we differentiate the whole thing, left hand side and right hand side, and the coefficient, this first one always remains the same. All right, so this becomes d2y dx2 plus, and then the second coefficient would always be just above this, which is p1, and then subtract this p naught, not just p naught, its first derivative. So this would be dy dx, then plus. So the next one would be just above this is p2, then subtract this p1 first derivative, right? And then plus, change the sign alternatively, then p naught. Now we have first derivative, so it is second derivative again. And then the left hand side is, when you integrate 0, then it becomes 0, but the integration constant should be there, which is c, and you call it c1 or c, any constant that you like. And then you will check this reduced equation again if it is exact or not. So if it is exact again, then you do the same process on and on after you get y, or until you get y. So that is how to solve an exact differential equation. And I think that would be enough for exactness. And if you have any questions, you can drop the equation or ask. So that would be all for this video.